Thought I'd start with the basic half-wave dipole antenna tuning theory. Probably saw this first in the technician study that you did. But basically, what we're looking at is at a dipole is nothing more than two wires that connect to a feed line that goes back to a transceiver. And some of the variables that you have to play with to get it to do what you want is the overall length of the antenna, which I designate here with a capital L, and then the element lengths, which I indicate by small l's. Now, in order to tune a dipole, you want to figure out where you want the resonant frequency to be in the band that you're planning to operate. And normally for single sideband activities, I like to put the resonant frequency right in the middle of the single sideband general band, the section at the top of the band. And there's a pretty well-known formula for coming up with the overall length of the dipole, where you take the what I call the magic number, and I only call it that because there is no magic. In this case, you'll see 468 and divide that by the target frequency where you're trying to put it, and it'll give you the overall length in the antenna. And then, being a dipole, since there are two elements, the individual element lengths are just the overall length divided by 2. Now, this 468 number is kind of it's a proportional constant that relates the length and the frequency. And what it covers is not only the things that drive the performance of the antenna, or the length of it, and the frequency, the resonant frequency, but there are a lot of other factors that work into it that impact this so-called magic number. It's the things that impact it include the height of the dipole above the ground, the type of ground the dipole is positioned over, the gauge of the wire enters into it, of the elements, and just a lot of other things that really don't contribute a whole lot, but they do have a little bit of an impact on how the antenna performs. So what we're going to do is take a look at what this formula is telling us, and we'll just go on from there. So here's the game plan. We'll use that theoretical model to design and build an antenna. And the antenna length, we'll figure out L1, this is the length of the first pass, is 468 divided by the target frequency that you're trying to set the antenna up to operate. L1 is measured in feet, and then each element's length will be just the overall length divided by 2. Then we're going to build and erect the antenna of this length that we just calculated, and then use an antenna analyzer to measure where the frequency, the resonant frequency is. And we're going to call that F res 1 for the resonant frequency. Then we're going to compute a new magic number. And the advantage of this is so much of what goes into this 468's unknown. What we need to recognize is that by going through step 2, we have enough information to calculate the new magic number, which is specific to the antenna that you just put in the air. And if you look at this formula here, if you multiply by both sides by the target frequency, then it becomes the new magic number is just the length that you calculated times the resistance you measured. And that's going to incorporate all the elements of that magic number for the particular antenna that you're working on. And that's kind of the trick to all this. Then, once we have the new magic number, we're going to go back and compute the new antenna and element lengths. So the new antenna length we're going to call L2, is the new magic number divided by our target frequency. The target frequency hasn't changed. And then the element length of the new setup will be L2 divided by 2. And then depending on the difference between the element length of the first pass that we did up here that we calculated here and the element length that we calculate here with the new magic number tells us whether we need to shorten or lengthen the elements of L2. So let's say L2 is less than the L1, the length we started with. Obviously that means we have to shorten it. If L2 is greater than the length we started with, then we'll have to lengthen it. And so what we'll do is we'll subtract the difference between L2 and L1, shorten or lengthen the elements to L2, and then we'll measure the resonant frequency after we've adjusted the length of the antenna and compare it to our target frequency. So I'm going to run through an example here kind of quickly. So what we're going to do is we're going to make the first approximation of the element length, which we use the formula we just looked at, the length being 468 divided. In this case, we're going to target 28.4 megahertz. That's right in the middle of the single sideband technician privilege. So we can try to hit that antenna right at that point. And the length that we come up with is about 16.5 feet. If we divide that by 2, then the overall length of the element is 8.24 feet, which is about 8 feet 2 3/4 inches. And that's what we're going to adjust the element to on our first pass. And then we're going to build and erect the antenna, however you're planning to do that. Now the second step, when we measure the resonant frequency after the antenna's up, is we'll make a note of it here. And then we'll compute a new magic number, which is just the length that we have the antenna. We know what that is because we just measured it out when we put the antenna together, times this resonant frequency that we just measured, and that'll give us our new magic number. I've kind of color coded the different things. The green relates to frequency, the red's the magic number information, and the blue is the length. And then just as a note, we're looking at the same target frequency, 28.4 megahertz. And then the new antenna, the new settings, the new length is going to be the new magic number that we calculate divided by the target frequency, and that'll give us the length of the overall antenna in feet and inches. And then we'll take that value and divide that by 2 to get the elements of the individual, or the length of the individual elements. And then looking at the first approximation that we came up with on the prior slide, the first length was 8 feet 2 3/4 inches. And then when we calculate the new L2 right here, we'll be able to compare these two numbers to see whether we need to lengthen or shorten the antenna, and by how much, because how much we're going to shorten the element is the difference between these two values. And then once we make that adjustment, we'll record the resonant frequency of the second resonant frequency. That'll be the result of shortening or lengthening the elements. And then we'll compare that resonant frequency with our target to see if it's close enough to what we want to do. So what I did is I used Alpha Antennas Hex Antenna. This is our go-to antenna for photo activations. Judy just loves this thing. And the thing that's nice about this is that they have telescoping elements that you can adjust. They're infinitely variable. You can adjust them to whatever length you want to cover everything from 70 centimeters to 40 meters. So what I did on the deck, here's an element that's not extended. I extended an element and laid out a tape measure and then adjusted it to the L1 element length that it calculated on the prior slide. And I'm showing you here we're at 98 3/4 inches length, which was the calculated length of the elements. So popped both of those elements on the tripod with the Hextena hub and set it up in the backyard. Then I used my the Rig Expert AA54 and the AntennaScope software to measure the response of the antenna and determine what the resonant frequency is. So we'll go through those steps we looked at earlier. First thing we did, do a measurement on the antenna, and with the lengths that I used, I came up with a resonant frequency of 28.08 megahertz. Now I'm going to compute the new magic number by taking L1, that 98 3/4 inch measurement, times this resonant frequency, and that tells me that the magic number for this antenna setting up in my backyard on the ground that I have and all the things around it, I need to use 462 as my new magic number. Then the target resonant frequency is still 28.4 megahertz. That's what we're trying to hit. And then the new L2, the length of the antenna with the new magic number, I can calculate by taking the new magic number and divide it by the target frequency, which is 28.4 megahertz, and I come out with 16 feet 3 1/4 inches. Divide that by 2, and I end up with an element length of 8 feet 1 5/8 inches. And the first approximation that we made from the first magic number, we had a length of 8 feet 2 3/4 inches. So that difference is what we're going to have to adjust the elements. So it's about an inch, right around an inch. We're going to adjust the elements, and we're going to shorten it 1 1/8 inch. Now the numbers come out a lot more precision than what you're going to be able to do with a tape measure. So it's probably going to be closer to 1 inch adjustment. We'll just have to see how it turns out, but you can't really get it real precise with a tape measure and the length of the elements you're usually dealing with. And then after we make that adjustment, I measured the resonant frequency, the second resonant frequency, at 28.54 megahertz. So I've got all that recorded. So we're at 28.54 megahertz with a resonant target frequency of 28.4 megahertz. And what I like to do now is take a look at the plots, the SWR and the phase angle plot, and kind of see what we ended up with. Excuse me. So what we have here, I've got the plot from the initial setup of the antenna, which was using the original magic number, and this is the SWR for that setup, and the resonant frequency is right here for that initial setup. So it's that's where that 28.080 came from. And then the thing I like looking at the phase angle, if you recall, the resonant frequency of a dipole occurs when there is no reactance, when the inductive reactance and the capacitive reactance cancel out, and you have no reactance, and you're at a zero phase angle. So with a phase plot, it's easy for you to find where you went to zero, and that's where your resonant frequency is, which just happens to be where this plot is showing it too. This just lets you be able to zero in on it a little closer on a graph. Then we shortened the elements, ran the frequency plot again, and you can see that the second SWR moved up in frequency because we shortened it, and you can see right here, here's the 28.4, our target, and this is where we ended up with the 28.540 or whatever it was, I forget the exact number. And you also see here where the capacitive and inductive reactance canceled each other out. Here it's capacitive reactance, and then this is where the resonant frequency is. So it's two ways showing the same information in terms of the resonant frequency. Now, rather than doing all that by hand, I put together a little Excel spreadsheet, and the conventions I use on my Excel spreadsheets is that any values you have to change, I always show as blue values, and everything else you should leave alone. So this is kind of divided into two sections, just like what we looked at. This section here deals with the first pass, where we use the 468 magic number, and we put in the target frequency. We calculated our lengths, or the spreadsheet did, and then we adjusted the antenna and measured the frequency and came out with a 28.08 megahertz. And then the second part is coming up with the new magic number, which we calculated to be 463, or the spreadsheet did, based on these values up here. And then the new antenna length, 16.29 feet, new element length 8.15, and we need to change the element length about a little over 1 inch. And since the new measured length is shorter, we have to shorten the antenna or the element, and this will tell you whether to shorten or lengthen it based on a little if statement in here. So we make those adjustments, we shorten it, measure our resonant frequency, and compare it to our target frequency. And my read on this is that that's pretty close, particularly as flat as that SWR curve is. You'd probably go crazy trying to tweak it in any closer. So that was a good fit. So we went from the theoretical length, took one measurement, we knew the length of the elements, and from that information we were able to come up with a better calculation of the required length, and we see the result we expected to see, where we did move the resonant frequency from out of our band there. Actually, this is out too a little bit on the high side, but it did move it to where we've got very good performance for this antenna at 10 meters in the middle of the technician single sideband. If anybody's interested in a copy of this spreadsheet, you can drop me an email. Now this is just something I wanted to show. The hex antenna, it's easy to adjust the length because of the telescoping elements, but when I build antennas, dipole antennas, I like to use this arrangement to make it easy to adjust the length, so you can do just the one adjustment and you're tuned in, that we just talked about. So it's just a normal insulator on the end with the antenna rope going to either a tree or however you're securing it with a mast. We've got the antenna element here, and I use these little U-clamps to secure the tuning stub, or at least that's what I call it. This is the extra length you need so you can lengthen or shorten the antenna. And then when you do your measurements, you want to measure when the antenna is extended to this point here, the farthest point. And if you need to shorten it, you loosen these up and you can pull this tuning stub the distance you need to shorten it, and then you can tighten the clamps back up. And if you're careful when you're putting up the antenna and leave enough rope on the end where you're securing it that you can lower the antenna, at least get the ends down on the ground. Since you don't have to measure the whole antenna, you can just do everything here because you're just shortening it typically a small amount. So that's about all I know, and hopefully this was helpful, and it should give you a pretty straightforward approach to tuning a new dipole, so you don't have to keep putting it up and taking it down. I've heard horror stories about guys that have had to go back and forth like that, and hopefully this will avoid those horror stories. So this is K3SKS 73 everyone, and I'm clear.